Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday we got rid of the C runtime library in our Win32 loader and mostly in our regular game as well in preparation for what I'm doing now, which is I'm going to be using sine and cosine today probably to work on our sampling quality. And what's going to happen is we're going to see that we really probably don't want to be calling sine and cosine C runtime library anymore because it's going to be slow. It's not going to be 4 wide anyway. Blah, blah, blah. So we're probably going to want to be able to call 4 wide sine and cosine, or even if we only call it 1 wide and then replicate, we're going to want it to be nice and fast and not slow like the one that's in the C runtime library. So we'll have to start looking at that next week, which is something we always want to do anyway, but it's, you know, finally at the point where we actually care. At least a little bit. And so that's what we're going to do next week probably. However, today we just want to go ahead and use our crappy sine and cosine that come with the C math library in the C runtime library, which we still link with the game. And if you remember from yesterday, we now know exactly the 6 routines we are using that we didn't write ourselves. We wrote everything in this game ourselves, except for 6 functions, or is it 5? Atan 2, cosine, sine, floor, and ceiling. So 5 functions. I believe I'm not, unless I'm forgetting one. So 5 functions that we haven't written ourselves. And we need to replace those functions with our own versions at some point. That's what we're going to talk about next week. For now, we can still do the work we were going to do using those functions as is, because we still have the ability to link the C runtime library. Basically, we can turn it on and off in the build. So I have it turned on right now so that the game code, even though the Win32 code doesn't link with it, the game code does. So that's where we're at. Let's go ahead and push forward on that. So here is what we stopped with. I made a, actually I believe it was a stream request at the end of the show yesterday, was to be able to draw the hemisphere as a little like set of points. So here is a stable sampling. So we're just looking at freezing the random number series at a particular point and looking at how it, you know, what the distribution over the hemisphere is. And what you can see about this is it's a totally reasonable random distribution over the hemisphere if what your goal is actual randomness, meaning unpredictability, right? It seems pretty unpredictable the way these points have been arranged. It doesn't look like there's a particular structure to them, so that's fine. But what we do see here is that it's not an even sampling. So remember we talked about white noise versus blue noise. What we're looking at here is something reminiscent of white noise. What we want is something more reminiscent of blue noise, which is to say that the points on the hemisphere kind of want to be placed in such a fashion as to ensure that any individual part of the hemisphere is not too far away from a sample point, right? We want to make sure that we sort of get coverage with our points. So we do want them to kind of wiggle around and get some sort of coverage over the entire hemisphere by randomly moving over every frame. But you know, by the same token, we want to make sure that they're spaced in a way that gives us some kind of a reasonable arrangement of points in terms of making sure no area gets completely unsampled on a particular frame. So we don't want big holes. And what we can see here is we do have those big holes, right? And again, that's not unexpected for white noise. White noise should be just as likely to have clumps and holes as it is to have an even distribution, because again, it's random, so there is no sort of bias or force pushing it towards uniform coverage, so we would expect that. So what we need to do is introduce that bias, introduce that uniform coverage constraint or something to try and keep it that way. So that's what we're going to look at today. And what we want to do here is we want to go into our lighting code. We want to go take a look at that part of the code that actually does the sampling. Here it is. And what we want to do here is we want to figure out ways we can make this routine generate more interesting stuff. Now, this routine can be as slow as it wants because we're just doing testing right now. So we can just be as slow as we want here and do anything we want to do here. So we're free to experiment, free to create whatever we want. And so that's what we're going to do, right? Now, if you take a look at how this is being set up at the moment, what we're doing here with our normal is we've got sort of a thing that picks random bilaterals, and it basically picks a direction and then picks a distance, how far it wants to go out along the normal in 2D, right? So we're effectively taking this process right here. What day is today? We're effectively taking a process that looks like this, where we take a flat disk. You know what, let me draw it a little more 3D so we can puff it out in a second here. So in the plane, you know, we've got a circle, and what we do is we're picking a direction in the circle. So we're picking like a direction like that, and then we're going to walk out along that direction a random amount. So, you know, here, here, wherever, right? Then we're going to project that up onto the hemisphere, right? Now what that's going to do, because of the way that it's being done right now, is it's going to concentrate our sample points more strongly in the middle than at the end. Why? Because we're walking out along a line in a uniform fashion, right? But that line is going to, spread out those points as it gets further away. So if you imagine two of these, right? Let's say you were going to take a bunch of these and place them like so. Well, let me see if I can draw it a little bit better here. Let's say we took a couple different lines, right? If each of these lines picked like 1/4, let's say, so those are our points, you can see that those points remain very close together. But if each of these picked 3/4, you can see that those points end up fairly far apart, right? So what we're going to end up having is less points on the perimeter and more points in the center. This was by design, right? This wasn't an accident. We meant to do this. Why? We want to concentrate our sampling in this region because we know the cosine law kills samples that are in this region. So rather than doing a lot of sampling towards the edges, we want to do a lot more sampling towards the center, right? And to a certain extent, that is what we accomplished. If you take a look at what's happening here, you'll notice we have a much stronger cluster up near the top. But the problem we get is that, you know, even there where there's a lot of sample points, they're still just clumpy, right? We got a big hole here and a big clump there. There's a big clump here, which is roughly at the same degree of fan out as here. So what we don't really want that. We want to see, as it gets further towards the end, much less sample points around that bend, right? Around that sort of end of the hemisphere, the ring. But we want to see it be even. So even any given band should be as sparse as it should be, dictated by how far down we've gone, proportional to like the cosine law, for example. But we still want to see them evenly distributed around the ring. So we don't want to see like tons of sample points on the right side and none on the left or whatever. And that's what we're seeing here, right? And again, that's exactly what we would expect to see because we don't do anything to prevent pure random white noise clumping, right? Which will happen. So let's think about what we can do here to try and improve the situation, right? All right. First of all, let's take a look at how many sample points we actually expect to have. That's our first step. So when we think about how many samples we'll probably have, you can see that our ray count here is 16, right? Which means if we multiply 16 by 4, we get 64. Which means that the number that we're using right here is actually accurate. That's how many we think that is the correct number we think we should be distributing. So our question now is, how would we distribute those 64 points in a reasonable fashion, right? And we do know also that we want to be casting 4 rays at a time. We want to keep those 4 rays that we're casting at the same time sort of pointing in roughly similar direction, right? So what I'd like to do here is I'd like to figure out a way to maybe do some regularized sampling and then maybe jitter within the regularized sampling. Now, if we assume that we have at least, so again, if we think we're going to be sending out 4 random samples per actual direction, then that means that we've got something that looks, like this. Right? Because obviously, if we go ahead and do 16 times 4, we end up with 64. So, or maybe the right way to say that is 64 divided by 4 is 16. So we know that we've got 16 primary directions to distribute, and then we've got 4, sort of packets of rays we're going to shoot out in a particular direction that want to be sort of semi-correlated, right? So what we want to do is figure out how we can sort of wrap these around. And actually, we may want to start with something because the person who did most of the code for Handmade Network, actually, Kalimian on the chat, I don't know if he's here, he was asking, maybe we could do spiral sampling, right? And I don't know, let me see, spiral point or... See if I can get a good... I wish I knew what to search for here. Sphere, spiral... I don't know, phyllotaxis is probably the right word for it. Let's see if we can get a diagram of this somewhere. So yeah, this is kind of like it, but it's not really what I wanted. This is more what I wanted, yeah. So if we want to take a repeating spiral and kind of put it down the sphere, that is what actually Kalimian was suggesting, and it's a pretty good idea actually of a way to quickly get something fairly distribution. It's on sphere. Just trying to find a good diagram here. Yeah, here we go. So here you can kind of see a 2D and a 3D version of this. Here is like a 2D, just looking at a disk, right? And they're referring to Vogel's method here, which is the way of like placing these points onto the disk, right? And you can see here how the points are produced in polar coordinates. So polar coordinates meaning almost exactly what I've written here, right? We take a direction and then we go out that direction by a particular distance. And so in this case, we're creating that direction by taking a random bilateral. In this case, we'd find that direction by taking a random angle and then using cosine and sine to figure out what it is, right? So here you can see what we've got in terms of the distribution. And I believe n is the number of points you want to do, right? I'm assuming, yeah, n is the number of points produced by the sequence. Theta is presumably the rate at which you want to spiral, I would assume. I'm not sure, though. Do they define theta anywhere? I don't actually see them say that. Here we go. So figuring out the ideal angle coefficient, right? They're saying this is the correct number of radians to use. It's the most irrational angle, I guess. I'm not sure what that means. But I'm sure that if Pseudonym73 were here, he would be able to tell us. Anyway, we can basically say that taking a particular theta, right, produces different kinds of spirals. And I guess, we're kind of saying that we want a nicely distributed one, so we're talking about ones that look like this rather than ones that look like this. Although, as you can see, it is a free parameter we can play with, which means that we don't actually have to think too hard about it if we know we just want to get one like this, right? They're sort of saying there is a rule you can use to arrive at that correct value. So that's how you would do it in 2D, right? That's the algorithm for producing this like sort of layout of points. And then, the question is, well, what do we do if we want to do these on a sphere? And they're basically saying, well, it's not really all that difficult to do. They use cylindrical coordinates, right, which is basically the same as polar coordinates, but then with a height. So these are very closely related. This is exactly the same as it was, so the angle distribution is the same. It's, but that's because this value is whatever we want to set it to, right? But then the TI here, where we do this, is actually going to be changed. It's going to be changed to use this ZI value, which is the height. So it's basically setting the distance we go out to be proportional to the height. But we end up with a fairly concise formula, again, for producing a set of spiral samples, and here's what that looks like. Now, what you can see here is it does look like a pretty nice sampling, right? It's a pretty good covering of a sphere without having to actually do real point repulsion or blue noise or something that actually produces a true random uniform covering. But, that's pretty good, right? We'd be pretty happy with that for 256 samples, certainly. Now, we only have 64 samples, so our sphere would be more sparse, unfortunately. And to be more concrete about that, actually, we only have 16 samples. But let's try playing around with this. I like the idea. I think Kalimian had a good idea here. Let's play around with this a little. We can start with this formula and play with this value to see what we get in terms of placement for our 16 points that we can then blow out to 64 using maybe jitter around the points or something similar, right? So I don't know. We can do that. The other thing we can do is produce these using the cylindrical coordinates, and maybe because we know how the cylindrical coordinates go, we could actually still use cylindrical coordinates for actually all of the points, and then know that based on your index, we could know which 4 to group that would be close together, right? So we could come up with some rule for tiling these that might be interesting. So we definitely have a lot of options here, and we'll kind of see. We'll see, right? All right. So let's start with this. What we want to do here is say, okay, we're going to be we'll start with just doing this many, and we'll sort of forego the subindex part for now. Like maybe we'll just nerf this. So we're literally just doing this part here. And what we want to do now is introduce a little bit of polar coordinates. So what I'm going to do is I'm going to do a random angle here. And this is corresponding to this part of the series, right? We want this pi here. We're going to be producing this value as an angle. So I'm going to switch to using a random unilateral here, and I'm going to say times tau 32, right? So basically, we're going to take a value from 0 to 2 pi, and we're going to produce that angle, right? Then, instead of normal being this, what I'm actually going to do is say it's going to be cosine of the angle, sine of the angle, and then I'm going to compile, right? So that should, in theory anyway, produce 16 points that are randomly distributed over the hemisphere in exactly the same way we were doing it before, right? So nothing else happening here. So there's our 16 points, and there they are on the hemisphere as we would expect. And again, that's just changing this into polar coordinates now. So now we have our sort of angle. Normal is a probably dumb thing to call this because we sort of kept that because we're using it the whole way through. But let's call this something a little bit different. Or maybe I'll start following this here, right? So this is our angle value, which is this p or rho, I guess that's the Greek symbol, right? For rho, not p, right? It's this guy. So anyway, so we could make it like so. And right now we're just computing that as a random unilateral, but then we will introduce the spiral in a second there. So we've got the rho, then we've got this TI here. That value is, again, kind of computed off of this. So we really want to start with this value first. So our z value in this case is, and this z value will get plugged straight in as a z, I believe. But we want this to be 1 over 1 minus 1 over n here, like so. And then that's going to multiply 1 minus 2 times I. Oops. And we're probably going to have to make that be a float here, right? Because it's going to be, I is going to be an integer, and we want to be doing these as floating point calculations. And then we're going to divide that. Here by n minus 1. And there's the complete equation. So we know that that's the equation for producing the z value. Let's go ahead and divide that out here. I believe that's right. Yeah. So then when we want to produce ti, it's fairly straightforward, right? It's just going to be the square root of 1 minus whatever that value is squared. And again, that's not actually t, I guess. Is that tau? These are tiny little letters. Yes, that's tau. So this is actually our tau value. I guess technically that means this is zeta, right? If we're really going for it. Nope, it's not. That's an actual z. All right. So now we've lined ourselves up with their nomenclature, which is good. All right, so this is going to be our square root here. And it's really just square root of 1 minus whatever that value is squared, right? So that's pretty straightforward as well. So again, this is the equations for setting up the spiral sampling. And presumably here, you know, if we want to kind of work this through a little bit more carefully, what's happening here is just that this is producing, you know, we know that this is the angle. So that's just telling us what direction we're going to go out. So here we're going to say how high we are. And so all this is doing is saying, well, if we're that high, here's how far out along the thing we have to go, right? So really all of the complexity here of producing the spiral has been baked into the height value, right? And if we want to, we can probably reverse engineer exactly how that works too, right? Because we know that it's supposed to be sort of producing a stepping around the sphere, right? So if you wanted to get a little bit more fancy, you could figure out exactly what we were doing here in terms of why we picked these particular ratios, right? But for now, let's just continue on with using the prescription for Vogel's method, which, by the way, should be, here it is. This is the actual method, and unfortunately it looks like maybe, I don't know if this actual paper exists anywhere in PDF form. Doesn't look like it necessarily does. There we go. So this is the actual paper. This is why they call it Vogel's method, is because Helmut Vogel, right? I don't know how to pronounce that. Vogel? Helmut Vogel? I'm not sure. My pronunciation of European names is pretty poor. So anyway, here is the actual paper that introduced this method. So this is probably actually the correct place to go if you really want to figure out exactly why the spiral is computed exactly the way it is. Now, I don't really care why the spiral is computed exactly the way it is, because again, I'm not really looking at this as an important feature. I'm looking at this more as a, like, what distributions have people come up with that are interesting, and Clemens stressed this one, it seems interesting. I don't really need to be able to edit this or make meaningful changes to it, so I don't really care exactly how it produces the spiral other than in an academic sense. However, again, we may want to get a little bit more into it later on, in which case we should decrypt these more directly and probably read that paper. So, taking another look, once we have these values here, again, this is not going to produce a spiral yet because this value has not actually been computed properly, so we're going to have to now actually make this be our theta value, which we haven't determined what that actually is yet, times our I value, like so. And we'll have to define what our theta is out here, right? So then we also have our other values like n, and we have our I value, which is, actually just this iterator here. And we've got our n value, which has to be the total number of points in the system, like so. And so the only thing we need to do now is actually compute that theta value. And then we've got the full set that was requested here. So in terms of the theta value, it looks like the theta value is actually used the same in this case. So it's the golden angle here times the n. So if we take a look at how that's actually be computed, this is the discussion up here, right? The golden angle pi times 3 minus root 5, it's roughly equal to, this value. The golden angle is the most irrational angle defined as 2 pi, whatever, blah, 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 right? So what we want to do here is just put in the approximation for it, because I guess we don't really care, we don't need it to actually be truly irrational in that sense. So what we can do here is actually just use it as it appears, right? Pi times 3 minus root 5 should be sufficient for us. So let's see here, 3 minus root 5. So that should produce the actual value that we want in theta. Again, we've got the number there, the 16, which is how many points we want to distribute, and then off we go. Now, I assume it's kind of interesting, right? We don't really modify this value. So, no matter how many points you're distributing, the distribution comes entirely in the later section. You always do the golden angle part here, right? Which is pretty bizarre. But that's just, that's actually the way... What is this little thing? Oh, syntax highlighter. So that's pretty interesting, right? I think that's pretty interesting. So anyway, again, if we take a look at just how this is computed, right, we don't... I guess I'm not sure exactly what this is meant to accomplish here, but you can see a range n. I assume this is just saying we're going to do this over a number of points. So I'm assuming that's still just I. But yeah, point being, it's interesting to note that this angle remains the same no matter what n is. Because normally in most distributions you would alter the theta based on the n, but here we don't. We only alter the placement, how far out we place it. We don't alter how much we rotate each time, which is kind of an interesting, if that's really the way these work, it's an interesting observation, right? About how those angles are behaving. Okay, so now if we want to actually produce the normal, well, at this point, we've pretty much got the information that we need. So we can actually stuff these directly if we want to. We know the angle that we're talking about here, and we know how far out we want to go, so we really can dispense with all of the rest of the stuff because we've already computed it all, and just directly compute a normal out of thin air, right? So using the values prescribed by Vogel's spiral formula, we can compute those values, and then we can see how they are arranged. And if you look at them, actually, they are quite nice, right? Those are very nicely evenly distributed over the sphere. And in fact, if we were to ratchet this up to the full 64 and take a look at what that looks like, that is a really nice covering, right? It looks lovely. Now, some things I would observe about that is it's for a sphere. So we do have a bit of a problem that the formula as written is giving us spherical data, not hemispherical data, right? So we don't really want the formula to behave the way the formula is normally behaving. So the n value that's used in here is not really the n value that we want. What we rather want here is double the n value, right? And the reason that we want that is because we want the n to stop at the hemisphere, not the sphere. So if we take a look at what would happen, for example, here, if I multiply that value by 2 so that we only run up to half of it, then we get the hemisphere that we wanted without completing the sphere towards the bottom, which is important, right? We don't want to have any points go to the downward facing hemisphere, because we're only currently sampling out away from the surface, not back in to the interior of the surface. If we were doing subsurface scattering, we would want that, right? But we don't. So there's the distribution of points prescribed by the spiral as suggested by Kalimian and discovered by Vogel in the 1970s. And I agree, that's a pretty nice start, right? I think that's pretty great. Now, again, if we go back to looking at what we actually have to work with in terms of points here, it's actually, oops, should just make that n. We actually only have 16 points to work with here. And so if we look at how those are distributed, those 16 points like this, we could imagine taking those 16 points and kind of fanning them out differently, right? So for each of those, if we did do a subindex here and we wanted to add random jitter to it, we could add random jitter by randomly jittering the rho and the zeta, right? Or the z in this case, right? So what I could do here is take this and introduce a random bilateral. And what we want to do here is add just a little bit of jitter. So, you know, we don't really know how much jitter we want to add because it's a pretty tough call. In this case, we know we're ranging up to tau. This is an angle, right? So it's proportional to tau in terms of how large it is. So this would be, you know, that would be 1/10 of the angle could vary. This would be 1/6 of 1/10 of the angle that could vary, right? This would be 100th of an angle, and so on. So I don't know exactly how much we want to vary it there. This is a height, so it ranges from 0 to 1 in this case. So again, we probably want this to be varying a little bit less than that. But exactly what we want, we don't really know. Let's go ahead and try those here. And so now we would have actual random coverage around each point. And we can kind of see how that is, right? And so those are not spread out nearly enough as what we would probably want in terms of getting sample coverage there. So let's go ahead and boost those up a bit just to kind of spread them out more. There you can see them spreading out. But again, still not really spread. Again, also now that we've done this, we need to normalize this. Again, in fact, you know what we can do is just move this down. So that'll should renormalize it for us, I believe, although it might not because of the way we're doing rho, but it probably should, right? Yeah, so there we go. So, you know, one of the problems, though, that you can see is this ends up getting back into sort of a more clumpy sort of problem there, right? So, again, we may just want to keep with the uniform sampling. I don't know, it's hard to say. But we may want to keep with the uniform sampling and then group back together to produce something more stable. I don't know. But it does seem like, also one of the things here is we probably want the angle to vary more at the bottom than at the top, right? So as the eye kind of gets further out, it's probably something more like, well, F32i over F32n times this random or whatever, something more like this, so that the variance in terms of the values increases as you go, right? Just taking a look here. So let's go ahead and make those values get a little larger there. And I'm also going to now take the training wheels off and allow this to vary so we can kind of see how the hemisphere is being sampled, right? So you can see that this point gets no spread, and the reason that that point gets no spread is because of this value here. So technically we would probably have to do something where we do an I+1 here just to make sure that, the ratio doesn't collapse at the very top. And that way this one can get some motion as well. But again, it's not fabulous. And you can see also, since it can't really rotate itself in terms of the way it's doing the displacement in the other equation, you don't get good sort of fan out there either. But either or, like, even just at this point, it's already, arguably better than what we were doing before. So that's kind of nice, but we still have a long way to go. So I don't really like the random jitter much, to be honest. I think this is kind of better. The question is, what can we do here? One thing I'm curious about is, let's suppose we just offset our row more, right? Like we just spun our angle by a random amount. So let's suppose that our row is just offset, is the only thing that we offset. And we offset the row by whatever we want. So it's just tau times a random unilateral. That's the thing. So we're just rotating this randomly. What kind of coverage does that give us, right? And if you look, it's pretty good, right? I mean, that's looking pretty good in terms of coverage there. You know what I'm saying? And if we, so if we were to do 64 samples this way, I think that would be pretty interesting. The problem is, again, the coherence of those samples isn't great, right? So let's go back to pausing this thing for a second and just talk about what I mean. So here is, oh, that's, wait a second. That's not what I wanted. No wonder it looked better than it should have looked. That's not what I wanted. What I wanted was this. I wanted to pick one random value and just jitter the sphere around, right? So it should look like that always, right? But then I wanted to jitter it around. So how's that coverage? Seems all right. Let's accumulate that coverage. So let's see how we do if we were to say, can we give ourselves a little more headroom here? Will this blow us up? No, that's just fine. So what I can do here is say, all right, yeah, let's go ahead and make this stationary. But then what I'm going to do is I'm going to run this multiple times. You know what? And all I really needed to do was this, I suppose. So let's do this 16 times. Actually, 10 times is probably better because I think our blend rate is like 0.1 or something like that. Actually, you know what? It might be 20. So it might be over 20 frames as our average. So let's just see over 20 frames what it will sample, right? So, you know, it's not awful, but you can see that you do get a little bit of a regular pattern happening here because you just can't seem to hit a bunch of these points. You know? We may also want to say, well, you know, this right here, this is the step function. So we may want to do something like this. And I don't know if that'll improve it at all, but probably not. Interesting. Am I doing something weird here? So I think, you know, maybe the better thing to jitter would be to jitter the actual I value. Because if we jittered the actual I value, then we would move along the spiral, which would give us better coverage, right? So this is probably a bad way to do it. What we probably want to do is maybe this. What do you think about this? So as we move through... Oh, and also, we're not actually tracking this properly because if we actually do this subindex here, the I values are not, are not accurate here. So if we actually wanted to do this, maybe this is the better way. Gosh, it's really tough to think about. All right, so let's restructure this loop a little bit here because I wasn't doing it fairly there. Because I wasn't updating the I properly. So let's back up a second. Rather than trying to be clever like I was doing before, let's forget about the fact that we need to bundle these for ray tracing. Let's just take a look at the thing as how the distribution is, and then we'll try to back figure out what to do about it, right? And you know what? Let's take out these F32s because what I can do here is just say, hey, these will just be F32s. So here we go. Now we've got, I think, the fairer test of this actual 64 rather than the 16. Let's take a look at that again now that I'm doing it fairly. So there's our 64 points, right? And now what I want to do is I want to jitter the I value. So this value here is what I want to jitter. So I want to take a random unilateral to push onto that. That'll basically offset us a little bit. Oop. So here's now the coverage. And you can definitely see it kind of biases towards the spiraling line, right? It can't seem to get... It doesn't jitter its displacement this way, which I guess makes sense, right? Because it's just making a spiral. Can we move this out of here? It's just making a spiral, right? It's just doing that. Whoa. What happened? Oh, I moved the thing over to the stairs. I always forget that we do that weird stair camera thing. Where are we? What's going on? We got issues. Let me rerun this. So taking a look, you know, it's not the worst distribution in the world, but it's not the best either. It's got just this heavy bias towards the rings, which you would expect, right? That is not unusual. But it does seem like maybe, so jittering the I at least is not exactly what we would want to do there. So I guess the next question is, should we do more of a traditional jitter on it? you know? So we could try that. So instead of doing an I offset value, let's try going back to the kind we were doing before, where we say produce the stable spiral. Because this is kind of what I'm hoping for. So now if I come in here, what if we were just to say normal equals nos normal? So I just do exactly what we were doing before. And add pure noise into there. And again, I don't know how much we want to separate those out. There we go. So that seems reasonable, right? Because those do seem to be growing in a sensible way. Let's see if we can make that work. Here's if they're 3 times larger. You know, that's not bad. It's not perfect. There's a fair bit of nonsense happening there, but it's not horrible. You know, it's pretty good. Let's up the sample count a little more. You know, it feels all right. You know, so I think that's not horrible. The other thing we want to do here is remember our I values want to be denser towards the top than towards the bottom. So if you look at it right now, it's kind of a uniform, you know, jitter in that sense, right? And you also kind of have this problem where as the spiral winds down at the end, you kind of end up with some nonsense happening there. I don't know if we want to try and fix that either. But so, you know, if we wanted to, in here, we could make this I be more proportional. So the I value that comes through here, where we're getting an index from 0 to n, you know, that maybe wants to be shifted so it's proportional to the cosine, right? So we kind of want that to be almost inverted, like so that the value is distributed opposite the sort of as it folds down. So what we could do here is say, well, you know, I don't know, maybe we square root this value or something so that it shrinks, it biases back. And we can adjust it and so on. But if you take a look at, you know, what happens there, and, you know, let me remove the sampling, the oversampling value, and just take a look at one. What you can see there is, like, hopefully we could make this sort of shrink back up to the top by changing the increment on I. Now, part of the problem here is that the theta value then becomes wrong. So it's kind of a little bit tricky to know how we would adjust that sampling to put more samples on the top than the bottom. Because as this equation doesn't really walk out along the spiral per se. What it does is it knows where it should put a point for any given step along the I, so they're kind of jumping around. So when we change the stepping on I, you don't get an even distribution anymore. Like, that's not really very good, right? Although maybe, you know, well, here, let's find out what happens. Yeah, like, you can see what ends up happening, right? As if you adulter those values, you get something very different. So that's a little bit harder. So I'm not really sure how we would want to address that. I guess one thing we could do is play with this value as well. But yeah, I mean, I feel like we'd have a hard time. I don't know. I feel like we'd have a hard time concentrating our values based on cosine theta. Unless I'm missing something obvious. I'm not seeing it. Now, granted, I'm not familiar with these distributions, so, you know, maybe there is an obvious way we could do it, but I don't know. So I may say, what if we just created a pattern that actually has the properties that we want directly? Because we could always reuse it, right? So let's think about that and see if maybe there's a way we can sort of say, hey, let's try something a little bit different. So let's suppose we went in here and you know, I could keep this guy. So it's, you know, still there, but I'm gonna go ahead and make another one here. So let's suppose we did something where we said, let's generate the points that we actually want. So here's the points. And we know we want, you know, 16 of them or something. Or maybe we want 64 of them to start with, right? And I'm going to keep a point count. And then what I'm going to do is I'm just going to say, like, all right, while the point count is less than the array count points. Again, it's super slow. Just doing super slow. I'm going to go ahead and draw these in a separate pass. So while I don't have enough points, I'm going to make a new point, or just, you know, a new point on the hemisphere. And I'm just going to do that 100% random, right? So I don't even care, do not care anything about this thing. Don't matter what the distribution is, it can be anything at all. The only thing I'm going to do is make sure that it's only pointing upward, because we're not actually making a sphere, we're making a hemisphere, right? So that's it. So just purely whatever, doesn't matter, scattered white noise, not even uniform white noise for that matter, because I'm doing a cube and then just projecting it onto a sphere. So just a complete crap distribution, and that's fine. Then what I'm going to do is I'm going to say, all right, let's just figure out how close we are to any other point, right? So I'm going to say, you know, I'm going to assume this point's valid. If the point is valid, then I'm going to say points point count plus plus, oops, plus, equals point count, equals p, and that's going to retire a point onto our sphere. So what I'm going to do for test index is say, well, if the points test index value, so one of the ones we've already added, if the length squared of the distance between me and one of the test points is less than the minimum distance, then it's over. So, you know, they have to be that close or something. I don't know, right? So this is just going to put random points on the sphere and guarantee that no 2 points are too close together based on this value that we set. So that will give us 64 randomly generated points. Off we go. Then I'm just going to draw them. And that's it. All right, so this is just an exercise of placing random points on a sphere and then discarding points that I don't want until we get a uniform coverage. Now, the key to getting the uniform coverage is to make sure that the point repulsion value there, that minimum distance, is sufficient. So I'm going to go ahead and adjust that value now, basically until our routine crashes. I know that sounds weird, but that's what I'm actually going to do. So you notice that gets a lot more random. Let's go one more time. You see a routine crash? Because now it can't possibly do it, right? We've given it an effectively impossible task. So we know that our answer is somewhere like this. So there's our lovely uniformly covered sphere, and it's quite nice, as you can see, right? It's pretty lovely, and off you go. Now, the reason I want to try it this way is because now what we can do is adjust the minimum distance, for example, based on where the point ends up height-wise, so that things down towards the bottom of the sphere are spaced further than things up towards the top of the sphere. And so what we can do is say something like, you know, this min distance squared equals whatever our normal minimum distance squared would be, times 1 minus the z value, so that basically as we get higher up, we are allowed to be closer, right? And so, you know, this is probably not, you know, it's probably more like 1.5. So, you know, how close do we want, how much bias do we want there? I don't know. But this way we can say, all right, you're allowed to clump pretty tightly at the top. You're not allowed. Don't ask me why I said minimum sometimes and min other times. I don't know. There we go. And so now we should be able to sort of adjust those values accordingly to make our points cluster more towards the top than the bottom. So let's go ahead and try adjusting those values towards something we want. So you can kind of see us starting to get that clumpiness that I wanted, right? And I don't know, we may want this to be a higher powered value too, right? Like you may want this value to get squared or square rooted. I think in this case, since the higher the value, the more it subtracts off, we would want to square root the value, right? To make it clumpier, I believe, don't quote me on that. Maybe I'm wrong about that. No, I'm pretty sure it should be square root, right? Although actually, I suppose if this is supposed to be proportional to the cosine weighting, so there should be cosine less samples at the bottom. So in some sense, I guess what we really want to do is shove this through a cosine, right? So what we'd really like to do is say, okay, cosine, so the cosine at 0 is 1, and the cosine at 1 is 0, so we really want that, right? I think. Oh, wait, no, that's wrong. That's not quite right. Since it's an angle, we need 0 to pi over 2, right? So if z is 0, then we will want the full minimum distance, so we will plug in 0. If z is 1, so it's pointing straight up, then we will have it return 1. I'm sorry, it will return 0, so you will use no minimum distance. Things can be as close as you want. That, I think, is correct in terms of allowing clumping, right? So now, in theory, if we increase that clumping value, I think that should do it, but don't quote me on that. But I think we should be able to clump more towards the top, hopefully. So there's a nicely clumped distribution, right? That falls off quite a bit as it goes. Now, I don't know if we really want it to fall off by that much, you know? Like, maybe that's too much. And so we may still want to bias that coverage value a little bit. So we may want to say, like, look, we need a little bit of separation. So we're going to always use a little bit of the minimum distance, right? Sort of as we go. And it will go up from there. Right? So then this has to be knocked back down again, and we have to, again, find that value. So this forces a little more repulsion at the top again. And now we'll see as we concentrate those points a little bit more. So it can't quite find them. So it's, again, something like this. So there's our clumping that's a little bit tighter now, right? And off we go. So let's try repeating this process, doing the whole sample count thing. To do this 20 times so that we'll actually see how ergogic it is, basically. So in here, I'm going to go ahead and initialize that hemi-series on the outside of this. So now this will like wiggle around, right? And that's what our coverage would look like over some number of frames, you know? So there we go. And on any given frame, you know, we know that it looks like that. So there's one option. And that seems to be a pretty good way to start, right? I don't know to what extent we could really do this. So, because we now have to produce bundles of points, right? So we could bundle these points up now, but then we kind of end up with this problem again of how do we deal with the sort of spread on the points? And that's a good question. So we kind of got to think about this a little bit. And if we were to reduce this point count to 16, and assume that each of the points was going to get 4 random fan-outs happening with it, what would our values be then, right? You know, that's what 16 looks like. Now it's worth noting that distance-wise, we're not using a particularly good measure for distance because we're using the Euclidean measure for distance, which will change quite a bit. So, and just to give you a little bit of an understanding of what I mean by that, so if you take a look at how the distance value is interpreted there, what we're talking about here is a hemisphere. So if we take 2 points on the hemisphere, I'm just taking the distance between them like that, which means that if you were to look at a cross-section of the arc that kind of contains them, I'm looking at that distance. But what we really would probably like to look at is this, right? How much angle is between them. And that may sound like fairly complicated, but it's really not, because remember, we know that if we have 2 normal, right? So if I have A and B, and I know that the length of A is 1, and I know that the length of B is also 1, then A transpose B is going to be length of A, length of B, cosine theta, which means that since these are both 1, I know that A transpose B is actually just equal to cosine theta. So I can measure the angle between them very reliably by just looking at the cosine, right? I know that cosine theta will give me exactly, will tell me exactly what I want. And furthermore, if I took the A cos, right, I would know exactly what the angle was too. So I can basically pick a minimum angle if I want to, right? And use that minimum angle instead as the comparison function. And that gives me a better, a more stable way to compare the distance between the points if I want to. Now, it doesn't really matter, but it's worth noting, right, that that's something we can do. And since we're going to do this in a pre-process anyway, because it's a slow process, we could trivially do that, and it makes it clearer what's actually happening, right? So what we can do is say, here there's a min cosine value, and that's going to be the cosine of whatever the angle is that we think is the minimum. So, you know, we don't know what that value is, but whatever the angle minimum happens to be, that's what it is, right? And then we have, when we go to do our this minimum distance squared sort of situation, that's going to become this min cosine, and the exact same thing will happen here, but we just adjust the minimum cosine instead based on where you are on the actual sphere. Then when you come here, what we're actually going to say is, yeah, not that at all. What we're going to do is the inner product of these 2 points, and we want to make sure that that inner product is going to be less than whatever our minimum is, right? So whatever that cosine value is, we want to make sure that it is less. Now, since we know that these have to be acute angles, we're not letting angles go past 90 degrees. We don't care about negatives here. So we also want to probably make sure that we didn't get an angle that's large enough in that sense. So what we need to actually do is change the way that this is phrased to saying we want to be above a minimum cosine. Now, why is that the case? Well, that's the case because as things get closer together, their cosine gets closer to 1, right? So we're actually looking to maintain things that are Wait, no. Let me say that one more time. I may still be correct. Uh, as, as things get closer together angle-wise, their value gets closer to 1, and we want to throw those out, right? So what we want to look at is I am correct. So we want to look at things that get above a certain amount, right? So we want to look to see, is this too high? And so we probably want to phrase this and say that there's a maximum cosine value you can have, because it's not really a minimum, it's a maximum cosine value you can have, right? Which means that this has to be phrased in a different way. This is not actually correct anymore, right? And so the maximum cosine value here, although we do have sort of our adjustment value, which is fine. We need to phrase this a little bit differently, because in this case, what we would rather do is we want that maximum cosine to get higher, not lower, right? We want to get higher as we go up the sphere, right? So the maximum cosine is going to be rather inverted from where it would have been. So instead, we're going to be doing something like, 1.0f, minus the c value. So in this case, right, what we're doing is saying, all right, look, if the c value is like 0, okay, so we're pointing like straight up, right? Is that right? No. PZ would be 1, and so that's going to be the full angle, so that would be 0, right? Our cosine value of pointing straight up would be 0. We want to use the fullest possible maximum, so we get the full range. As it comes down, right, and we are plugging in a 0 there, which will give us out a cosine of 1, we therefore want to force very wide angles at that point, right? So maybe not 1.0, like still again, maybe we give it that headroom or something there, but something like that. It's going to be closer, right? So then we just say, all right, look, if you dot in there and you end up with more than the maximum, you're invalid and we're going to throw you out. Otherwise, we will keep you and it's good, right? So let's go ahead and take a look in here and start updating that constant value. And again, this is the exact same process we did before. Nothing mysterious there. Just using a different error metric for how or a different distance metric for how close these points are, which should give us slightly fairer results. Again, I don't know that it will necessarily matter in practice. It's just sort of a using the truer measure, the one that would be is more logical for our situation, so that we can just have a cleaner result there, I think. All right. So there we go. There's our distribution of points. Again, pretty even on the sphere, and this time based on angle. I want to sort of be able to clump those towards the top more, and I don't feel like I'm getting enough of that at the moment. So I don't know if maybe we need this to kind of drop down a little bit. Oh. That's because I wasn't using it. All right, so now let's try to spread these out a little more. Again, we want to keep clumping at the top as necessary. This doesn't seem to be producing much repulsion here. So clearly this is not falling off the way that I think it should be, or something. Well, okay, so this would do a cosine squared fall off. So I guess technically what we really want to do is this. Right? So we actually want the cosine value probably to be put in here. So that the maximum cosine as the z value, yeah. So, you know, this z value, right? Let's talk about this for a second. So this z value is going to go, I guess I'll leave that in there. This v value here will now go from 0 to half pi. So the cosine value will go all the way up to 1 as the, will go all the way to 0 as the z value gets to 1. And it will be, when the z value is actually 0, so it's down at the bottom, it will actually be 0. So the maximum cosine is anything that's 90 degrees, right? So we can kind of adjust this now by saying, you know, whatever this value is that we put in here, maybe we probably don't want it to quite be that aggressive in terms of what we plug in angle-wise. So let's say we have a minimum angle that we want to have happen there, right? So let's say we want a minimum angle of 0.1 radians. Oh, well, that's not 0.1 radians, sorry. 0.1 pi radians. And then we want to use the 0.4 as the rest of our cosine range, right? And that's how we're going to set up our angle, you know, based distribution there. So let's play around with this a little bit and see if that maybe gets us more what we were looking for. So, and am I going the right way there? Just want to make sure before I start trying to tune this. Am I going the right way there? Again, as z gets larger, we want our cosine value to get smaller. And that, yeah, and so that's not going to happen, right? Because we want, if this is 0, we want the output to be close to 0, right? So we actually want that to be minus. We have that going the opposite direction. All right. So let's take a look, and maybe that's too much, right? In terms of max cosines there. So we may want the thing to never quite get there, right? We may want something more like this. Still not quite right. So yeah, if we could say that. What am I doing wrong here? I feel like this should be okay, right? Because the maximum cosine value here, you know, as we want it to be close to 0, right? I mean, if we put cosine 0 in, the max cosine would be 1 and nothing would be over it, right? I mean, let's suppose we just do this. No weighting at all. So that angle's still too large, apparently. And that angle isn't. So that angle is supposedly our neutral angle, right? Like, that's close enough. So now if we actually went in here and said, well, okay, as you get closer to the top, you should get even lower. This should definitely work, because now you have even more room, virtual room, to place these points, right? At least I would think so. So I should be able to increase this value. So it still feels like it should be able to go a little bit more than that in terms of repulsion. I also think actually clumping wise, let me actually... So that's starting to look pretty good. So 392 did not work, right? That was crashy. Yeah. Should write a little program that just finds out. It just like, for any given value, figures out where the crash point is. Two point eight. So I also want to try upping the sample count here so I can see what happens over several frames, like what we end up with. And I'm not really sure why we're getting that kind of somewhat clumping behavior there. I don't know if that's somehow related to the way we're doing the randomness, or if our random number generator, because it's an XOR shift, just isn't good enough. That I really just don't know. So it's kind of difficult to say what should be happening there, right? But it feels a little off. If we do aggressive oversampling, so much more so than we would expect in practice, how does that look? Does it still have them? I mean, it's tough to say because it's one of those things where you're like, maybe that's correct. It's really hard to say. It may actually be, though, that the XOR shift really does want to be modified, because the XOR shift may have problems with successive values not producing good pairwise values. So we may want to look at that a little more carefully, right? Because that could be affecting us there. Yeah, it's hard to say. So anyway, what we could do now is take a look at what would happen sample-wise if we did something slightly different, which is to say, we could say, let's keep the sample count here as 1, and then instead what we'll do here is we'll do 20 samples of the samples we have with a displacement. So we'll say that the normal equals normalizer 0 of the points, point index and for each one of those points we'll do a displacement. Actually, you know what? I'm just going to do it this way. Oops. so if we take a look at this displacement-based method here, so we'll say, all right, let's suppose that for each of these points, let's suppose that we did a random displacement around the points each time and draw what that looks like. And furthermore, we can do 20 times 4 because that's roughly how many samples we'll take. 4 per, every ray will be a bundle of 4 and we'll do it over 20 frames. It's kind of what we were doing before. What would that look like if we put a little bit in there? Oh, you know what? That's way too much randomness though. I don't want it that random. So here's what that would look like. And again, you can see sort of the random patches spreading out a little bit there. And so if I go ahead and make those random patch spreads be, a little bit wider, you can see that it's actually relatively good in terms of coverage there. It's not too bad. But, yeah, could it be better? Probably. What we could also look at here is this spread wants to be based on the Z to a certain extent. So we want to, do something probably more like this. Where we have some sort of minimum displacement, and then we're going to get some amount of displacement from the Z, so that things on top, which are supposed to be clustered closer together anyway, get less randomness added to the, less spread to their samples than ones that are further down, which, maybe have to get more. So as the Z gets lower, we want more. I guess that actually means we want this kind of a thing, right? So we get the maximum when Z is lowest, and the minimum when Z is highest. So something like that. I'm not sure exactly how much, that should factor in, but something like this. Seems not too horrible. And if we take a look at one of these, again, just so I can understand what would happen if, oops, to just one of them, how bad is it? We want to make sure that it's still fairly uniform for any given one. So actually I guess that's 4. And so that really doesn't help us much with the uniformity if we do it that way, So I kind of think it may be a losing battle to do it that way. I think we're gonna have to distribute the 64 points as 64 points, and go from there, which is not fabulous, but I think that's what we're gonna have to do. And then we'll just have to figure out a way to randomize those much more tightly, or jitter them much more slightly than we were. I'm not sure, but it doesn't look good for doing them in sort of a 16 then random 4 way, which is what we would have liked, but it doesn't look likely. Okay. So let's take a look here. We need to adjust this then for doing a full 64 point distribution because this is going to be too much spread for these. So generally speaking, we need a wider angle. We need to make max cosine be a lower value. So the value inside has to go up, right? We have to get this value to be higher than it should be, right? Or I should say higher than it sorry, this value needs to be lower so that the max cosine will be higher, right? So, this has to get knocked down. I'm not sure to where exactly, but, it has to be knocked down significantly, so we can just do a quick test to see. All right, so there's 64 points repulsion-wise. Let's go ahead and knock this value down a little. Ooh, that's, nope, not what we wanted. That's what I meant. And maybe we can go ahead and notch this value up slightly. All right. So let's take a look at this distribution. See what we think of it. So that does look pretty nice, you know? I think I'd be happy with that. Yeah, and that seems pretty good. So what we could do next time is we could then try to bundle these into ray bundles that make sense, right? So, try to cast like those four together and those four together, whatever, or those four, right? Try to produce segments on this that are, as closely, as compact as possible to maximize the chances that they traverse and hit the same things. So let's go ahead and do a quick Q&A, and then we'll finish up that, because that's about all the time we have for today. What do you think about a compile time switch to flip between pseudo RNG and standard RNG to see if it's an RNG issue? I'm sorry. What's a standard RNG? I'm not sure I know what a standard RNG is. Nixie, why can't we use the spiral method to generate 64 points that we group into 16 groups of 4 based on direction and then rotate the spiral 18 degrees over 20 frames to samples? The reason is because that won't cover the hemisphere. Like, remember how it produces sort of steps along, and if we rotate them, it will just produce slices like a peeled orange. So we need ways of displacing our points laterally as well. And I'm not sure exactly how we want to do that yet, but we definitely need jittering more than just rotation. We need to jitter vertically as well, if that makes sense. What about a pre-computed sample sphere that you rotate over the frame period instead of random jittering? So again, rotation doesn't help us. The problem with rotation is that we need to rotate on all axes, and then a part of our hemisphere would kind of dip away, right? So remember, let's say you take a look at a particular cross-section of your sphere, right? And you've got points here, here, and here, right? Well, rotation does give you the coverage this way, but it gives you no more coverage this way. So if there was no point in this region anywhere in the ring on your initial random distribution, rotating it won't cover it, right? So you need ways of doing lateral displacement as well. And so we need our scheme to have lateral displacement as well. Does that make sense? And that's true for the spiral as well. The spiral will never give us what we actually want unless we jitter the spirals. Yeah, I mean, the spiral is a hard distribution to think about. I feel like it's kind of not one I really want to use, largely because I feel like it would take a while for us to intuit it. Now, if we actually sat down and really studied it, then I think we could play with the formula and make it work. But I'm just not sure about that. Off-axis rotation will cause our points to dip below the hemisphere. So one of the problems is we need it to never be in the bottom hemisphere. If we do an off-axis rotation, some of the points that were low will cross into here, and that's unacceptable. We definitely can't have that, because then we're casting backwards into the interior of a volume, which we really don't want to do. Hopefully that makes some sense. So yeah, you know, I don't know that we maybe the right answer is to kind of like maybe the right answer is to study the spiral formula and make it a new adapted formula that's basically the same as the spiral formula that allows us to produce randomly spaced points in a specific way that we want, that allows for the jitter, but I don't know. I mean, yet another way to do it would be to just produce quadrant-based stuff where we just divide the sphere up into 64 slices that we then randomly pick one point inside, right? And that might be good, right? Best allies, the CRT's random number generator is complete garbage. So you wouldn't compare against that one if you were. You'd have to go get. We'd have to maybe implement one of the PC RGs, like from O'Neill's paper or something, because the C runtime non-biased random generator is like the worst one ever. Those are linear congruential generators, which are complete garbage, right? In fact, I can show you. Like XOR shift is better than the C runtime libraries one, if that makes sense. Where is that? This is not what I want. That is not what I want at all. No. False. Incorrect. This is so annoying. Is this right? No. Still not right. There we go. That's what I actually wanted. And now, so let's see if we can get a rand in here. Come on, there's got to be a rand in here somewhere, folks. You know what? Forget it. Okay, are we ever going to actually... So I think... This is it. Maybe not. How is this the... Is this really random? This is nuts. This looks more like it. There's the mul, there's the add, there's the shift. Well, I wanted to show you the source code to it, but unfortunately all I would be able to show you is the assembly, but it's just that's all it is. It's a multiply, and add, and a shift for a linear congruential generator. So that was the code right there for it. And so it's not like some good random number generator. It's just this. Right? That's all it is. And you don't need to do the modulus, because if you're just using the entire number range, this is what you do afterwards to produce a particular random between some number and some other number. So it's just this, right? And then well, I guess this is probably the shift, right? If you're doing one that's just uses a power of 2, then it's just a shift, right? Unfortunately, yeah, we don't have the source code to the MSV CRT to show you that that's just what it's doing, but that's what that's what it was, right? Long boolean. Is this intended as a pre-process step, or will these hemispheres be computed for every quad, every frame? It'll probably be a combination of two steps: a pre-computation step and then a per quad step. And so we have to keep the per quad part simple, but the pre-process step can be as complicated as we want, really. Could anything be done with a centroidal Voronoi tessellation covering the sphere? Is that too expensive? Is it a terrible idea? No, that's sort of what we're talking about. Like, once I've produced these points on the sphere, you know, maybe we produce regions that are sort of like a Voronoi region for each one of them, and we randomize in between those, right? So I don't know. We'll see. Could we get a relatively performant blue noise? Yes, you can do a relatively performant blue noise. I'm doing the simplest way of producing blue noise, but there's a lot of ways you can do it faster. You still wouldn't want to do it for every quad, no matter what you do. But you can do it much faster than what I'm doing. In fact, I even have a thing I talk about that on my blog, in fact, when I was talking about the witnesses grass sampling thing. So I think it's in here. Yeah. So here is, you know, the way that we're doing it in Handmade Hero right now is this graph. And this is the graph of, it's the same as this graph and this graph are the same. It's just a scaled version that includes the highest point, right? And so here I talk about how you get rid of that. Here's the graph of, you know, if you write the algorithm properly, of how many test points you need per point inserted. And you can read about that here. So it's just blog entry number 10. So, all right, I'm going to wrap things up. Thank you for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. Next weekend, well, I guess we won't have to replace cosine and sine just yet because we still have more stuff we can try just in terms of getting our hemisphere sampling the way we want it. So maybe next weekend won't have to happen. But, you know, as you can see, we've got sine and cosine in there now. We don't know how much more we'll have to do with it, but you know, we're definitely getting to the point where we want to replace it anyways because it's, you know, it's happening. It's being used for real in the code base now. So we want to get rid of the C runtime library, and that's something that's on the hopper. But we can do more because we're only using the pre-computation step now, so we don't really care how fast it is, and maybe we end up only using it in the pre-computation step in which case we really don't care how fast it is, and it won't force the issue. But either way, we've got at least one more weekend we can do without having to replace it. So next weekend we'll play around with the sampling a little bit more. Hope to see you back here for that. Until then, if you want to follow along with the source code, you can always pre-order the game on handmadehero.org, and it comes with the source code, so you can play around with your own hemisphere sampling and see if you can come up with a good hemisphere to sample for our lighting purposes. That's about it for today. Hope to see you back here next week. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.